So far, we covered OMP. However, OMP suffers from multiple disadvantages. First, it is non-convex because of the L0 pseudonorm. Now, it makes the identification questionable because maybe if we just check any possible option for the sparse representation, maybe we would find a better representation that is not necessarily by the order of the atoms or the features identified. Another disadvantage is that it's very computationally expensive. It requires a lot of iterations and a lot of computations, and that's why it also takes a lot of time to compute. In addition, the major maybe limitation with respect to neuro AI is that we often don't know what are the features. In OMP, we assume that we have the dictionary of features and only find its sparse representation. However, in real-world applications, we often don't know what is this dictionary, and we would like to find it as well. That's why we have dictionary learning. In dictionary learning, we also learn the dictionary. In particular, let's assume that we have some output signal, and we want to find the underlying latent features that their sparse representation can reconstruct the signal pretty well. We would like to basically identify the features themselves. So from the signal, we would like to identify the hidden features. It can be either, for instance, time signal, or it can be image. Okay, so it's possible that we have some image and we would like to identify the underlying components whose sparse representation can build the image. So this is what is also assumed to happen in our visual cortex. So first, we will focus on the MNIST data. The MNIST data include a lot of handwriting of different digits, and we created for you a short video of multiple sparse combinations of digits evolving over time, and the weights or the contributions of different digits over time to the video change over time. So here we have a sparse combination, for instance, of 3 digits, and for a summation of them, we can get the value in the video. And over time, we may have different combinations. So you see how combinations of digits evolve. And we would like to identify the underlying dictionary of digits through this video. So your exercise now is to take the code that we prepared for you, where we define the video. We define some lower resolution video so it will work faster. And here we define some object called dicklearner. This dicklearner is basically the basic algorithm for dictionary learning. It will learn the dictionary and will also learn the coefficients or the contributions of different dictionary components to the movie over time. And you have to fill in the fit transform functions and basically train this object on our video in order to be able to find the underlying digits as well as their sparse representation. So when you observe your result, you should get the following digits. You see that we can really identify which digit each of those images refer to. Basically, our algorithm was able to recover the underlying components, the digits themselves, whose decomposition creates the video. When we look on the activity levels of these images, you can see that different digits contribute to the video over time. So here we have this atom, and in different time points we have different atoms or different basis images active. In contrast, when we look, for instance, on PCA, which is not sparse, we get the following components, which are not really meaningful.